So I will be presenting an efficient way of implementing the k-nearest neighbors algorithm. Now, before jumping into the code directly, I would first summarize the algorithm here. And if you want to learn more about the details of this algorithm, you can check out my previous video. The link is in the description. So when you're implementing k-nearest neighbor algorithm, you're given n data points. Let's represent them by x1, y1, x2, y2, up to xn, yn. And you want to make a prediction for a test point x, which doesn't have a ground truth label associated with it. Okay, so what you would do first is compute the distance of this test point from these different training points. So let's represent this distance by d1, then you can have d2, and finally dn. So to identify the k nearest neighbors of this test point, you would first need to sort the distances, and then once you've sorted these distances, you identify the k nearest neighbors. Now the most expensive part of this operation is the sorting. Okay, so if you have n points, then sorting the n distances that you have will scale with n log n, and this could be very expensive when n is extremely large. But there's another more efficient way of implementing k nearest neighbors, where the complexity reduces to order n log k, and this scaling with n is certainly more desirable when n is large and k is relatively small as compared to n. So that's what I will discuss in this video. And the way we would achieve this complexity is with the help of something called a MaxHeap data structure. So the MaxHeap data structure, I will not be discussing this in detail, but I can present to you an example that really summarizes what this data structure is about. So let's say you have 5 values, 0, 1, 2, 3, and 4, and you put them all onto a heap, onto a MaxHeap. So what MaxHeap does is that it constructs a tree out of these values. It's a tree-based data structure, and this is how these different values will be placed along a tree. So you'll have 4 on top, then you will have 3, 2, and then 1, and finally 0. And the idea is to have values stored such that all the descendants of a particular node have a smaller value than the node. Right? What this means is that this node has a value 4, which is greater than all the other values of its descendants. So the descendants of 4 are these nodes, and all of them have a smaller value than 4. You can pick also another node. If we pick 3, for example, then 3 has a higher value compared to all of its descendants, which are shown here. So that's the main idea behind MaxHeap data structure, and obviously you can also do it for more values than shown here. So we will be using a maximum heap data structure to implement the k nearest neighbor algorithm. So now I will present with an example how the MaxHeap data structure can be used to implement k nearest neighbors efficiently. So for simplicity, assume that that n is equal to 5. So you have 5 training points, and you're looking at 2 nearest neighbors. So k is equal to 2. And same as before, we store the distances in a list. So we use the same distances as before, and you can see that I've kept some space here, and this space I will be using to store the labels corresponding to the different training points. Say this label is 1, 0, 0, 1, 0. So I'm assuming here that you're using k nearest neighbors to solve a binary classification problem. So once we have identified the 2 smallest distances, we don't just need the distances. To construct the k nearest neighbor approximation, we also need to average, or in this case take the majority vote of the labels in our neighborhood. And that's why, in addition to the distances, we need to keep a track of the corresponding labels. You will see this in a second, where these labels are helpful. So the way the algorithm works is that we will loop through this list of distances, and at any given iteration, let's say you're here, at any given point in your for loop, we will be maintaining the two nearest neighbors we have encountered so far, and these two nearest neighbors will be maintained with a maximum heap data structure. So let's say we are at this point, which is 4 comma 1. We will push this point onto a heap, so the heap will now contain 4 comma 1. Then in the next iteration we will be at 1 comma 0, so we will push this again onto the heap, and since 1 is smaller than 4, we are only comparing, remember that we are only comparing the distances. The second entry is just to keep a track of the ground truth label, and the second entry will be used by the data structure only when the distances are the same. So if instead of 4 we had 1 comma 1, and then we were pushing 1 comma 0 onto this maximum heap, then the maximum heap algorithm would compare 0 to 1. That's the second entry. But when the distances are the same, right, then we can choose either of these ground truth labels, and it doesn't really matter whether we choose the bigger one or the smaller one. But the comparison when the distances are different is only done based upon the first entry, which stores the distances that we calculated. Okay, so to go back to what we were discussing, in our for loop iteration we are at the second entry, and we will add 1 comma 0 to our heap since 1 is smaller than 4, and then in the next iteration we will be at the third point, and again we will push it onto the heap. So the heap would now contain 3 elements. Now, because the maximum heap has 3 elements and we only want to store the 2 nearest neighbors, we need to remove a particular node from this heap, and the node we remove would be the one that has the maximum value. So we would be removing this root node, and that's where maximum heap data structure is very useful, because removing this node can be done in order 1 operations. So as soon as you remove this node, you will just be left with 1 comma 0 and 0 comma 0. So now we are at the fourth point, and we will add that to our list. So we will have 1 comma 0, 0 comma 0, and since 2 is the largest distance among these two distances we have, so 2 comma 1 would go on top, and 1 comma 0 would be moved to the bottom. Now you can see that what happens with maximum heap is that the maximum distance always sits at the top, and that's why it's very easy to kick that distance out and always maintain a list of k nearest neighbors. So we will do the same thing again. We will check whether the size of the maximum heap is more than 2, and indeed it is. So we need to pop out or remove the maximum distance. As soon as we do that, we will end up with the same maximum heap that we had earlier. So the heap now would be here shown on the left, and then at the last iteration we will be at this point, and the same would be repeated. So 3 comma 0 will be added to the top, and then you will check if the maximum heap has a length of more than 2, and indeed it will. So you will kick out the maximum element, and the maximum element will correspond to 3 comma 0. So you will end up with the maximum heap that is shown here, and you can check that 1 comma 0 and 0 comma 0 are indeed the two nearest neighbors that we wanted to identify. So the two minimum distances in this list were 1 and 0. So this example summarizes how the algorithm works, and obviously the same technique would be used even when you have larger number of data points, or if the k is larger than 2. Now let's discuss why the complexity of this algorithm is order n log k. Now this list we had contains 2 elements. One is the distance, and the second entry is the ground truth label. Okay, so if you were to formulate this, if we were to formulate this list for the general setting, then we would have something as follows. So you'll have d1 y1, d2 y2, up to dn yn, and if you remember, we loop over this entire list, and this is what leads to this complexity of order n here. And this log k is coming from us pushing each of these elements onto the maximum heap. So the time complexity of pushing an element onto a maximum heap is order log number of elements in the heap. And um, and for the implementation that we have, the number of elements never exceed k. If you remember, what we did in this example was, as soon as we added this third element onto the heap, we questioned whether the number of elements in the heap are more than k or not. And because they were more than k, we popped out the maximum element from the heap. So at any given point, when you're pushing an element onto a heap, the size of the maximum heap is never greater than k. So the final complexity, the final time complexity, is therefore order n log k. Now with this in mind, let's jump onto the code. So let's look into the code now. What I've done here is copy pasted a few libraries we will need. The first one is NumPy, which is standard for linear algebra operations. Then you have the random package from NumPy. This takes care of sampling random numbers, shuffling them, etc. And these other libraries, these will be required for plotting. And the last one, which is heapq, this one we will be using for implementing maximum heap in Python. And this statement here, which sets the seed for our random number generators, this makes sure that there is reproducibility in our code. So the whole code is split into two parts. The first part is a class which we will use to generate our data set. And here I will be using the exact same class as in my previous video on linear regression. I will be copy pasting this class from my previous video, and I'll just walk you through the different parts of this class. So this class is called data generator, and this takes as input the distributions for our input features. So our feature is two-dimensional, and the first dimension, the component along the first dimension, is denoted by x1. The second component is denoted by x2, and both of these components, they follow a beta distribution, and the parameters of this beta distribution are given by these input parameters x1 power and x2 power. Then we have a function that generates the label. So the label follows this relation where you have a sine function that operates along the first dimension of the input, that's x1, plus you have a cosine function that operates on the second dimension of the input vector. And then finally we have epsilon. So this epsilon here captures the noise in our label that we might have, and the noise is distributed normally with mean 0 and a certain standard deviation. So the standard deviation here is also an input to the initializer of our class. Next, we have a function that generates the training data. So this function is very straightforward. You just generate samples of x1 and x2 from your beta distribution, and then you use those samples to generate your labels, and finally you store them in an array. The rest of the next function, which is related to plotting, basically plots the data samples that we have collected. And the final function is also very straightforward. You just take the entire data set and you split it into training set, which you use for training the model. Then you have a validation set, which you use for tuning hyperparameters. And finally, you have a test set, which you would use to report the actual performance of the model, because if you just directly use the performance on the validation set, then there might be some bias associated with it because you might have used it for hyperparameter tuning. So these are the functions that we implemented also last time, and I'll just be using them without any changes. So we can now initialize this class and run it. So we will be initializing with the different, first we will be initializing the different parameters of our beta distribution, and this also I'll be copy pasting from my previous code. So we chose these parameters for demonstration purposes. You can also use any other parameters if you wish. And the next step would be to generate the different data points, and this we do via the generate training data function. And finally, I think I forgot to load the libraries. And finally, we can plot the different data points that we've generated. So just like the previous code, you'll have a sine wave along the x1 direction, and along x2 we have a cosine wave. And once we have generated the data set, we can split it into a training, validation, and test set, which is done via the split dataset function. So as you can see, I'm keeping 70% of my data points for training, and the rest 30% goes into validation and testing. And I have an equal distribution for both validation and testing. The next class would be a fit model class, where we will be fitting k-nearest neighbor model to the training dataset we have generated here. The first step would be to initialize this class and store the number of neighbors in kNN that we want to choose. The next step would be to define distance between two input features. If you remember, this is the distance that we use to identify the k nearest neighbors. So we have the class itself, and we have one particular input feature, and we have a test point x to which we want to compute the distance. And here we will just be using the Euclidean distance, the Manhattan distance, where we subtract the two features and take their absolute value, and finally we sum them up. So if the feature is two-dimensional, then this function would return to us x1 minus x, the first component of x prime, plus the second component of x minus the second component of x prime, where x prime here is the second vector and x is the first vector. Okay, so now that we have the distance function, we can implement the k nearest neighbor algorithm. All right, so the first thing we will do is implement get kNN, where the get kNN function returns to us the k nearest neighbors. Okay, and we will do that with the help of a maximum heap, as I said before. So the input to this function are the training points and a test point x. First, we would collect the distances of this test point x to the different training points. So we'll call the get distance function on one input feature x train, and we measure the distance with respect to the test point x. We also have the label corresponding to this training point, and finally we loop over all the different training points we have. So I'm going to enumerate x train. Okay, and one thing I would like to point out is that we are storing the negative of the distances, and the reason for that is because we don't have access to maximum heap in Python. So what we need to use is rather a minimum heap, and minimum heap with negative distance value is equivalent to a maximum heap. So once we have these distances and the labels, we will define our maximum heap, and now we start looping over all the entries in the distance label pair. Okay, and as discussed earlier, we will first push these entries onto our heap. So we push this with the help of this function from heap queue, and then if the length of our heap is more than the value of k, then we pop the maximum distance, or the entry corresponding to the maximum distance. Right? And finally, all we have to do is return the labels corresponding to these nearest neighbors. So we will loop over the different entries in our heap, and we return the second element of each of these entries, because that's the label. If you remember, the first entry was the distance that we computed. Okay, so once we have this function, we can implement a get prediction function, which actually computes the prediction by averaging out these different nearest neighbors that we have identified. The input to this function is again x train, y train, and a set of test points, only the input features. We define an array in which we will store our results, and now we start looping over the different test points. the first step is to compute the nearest, the labels of the nearest neighbors, and this we do with the help of kNN function. And once we have all these nearest points, we just need to take their average, and that's done via the np mean function. So we take the mean of nearest y, and that's it. So once we've done this, we can just return the predictions in the form of a numpy array. Okay, and so this is the core of the fit model routine, and all that is left to do is to implement a function that computes the mean squared error and plots the approximation that we have. So the next function we will implement would compute the mean squared error, and this is how it looks like. So the mean squared error function would take as input the ground truth labels and the predictions. Once we have these two quantities, we'll compute the difference between the two, and finally we would return the mean squared error, which is nothing but a mean of the square of these distances. So we take the mean function from our numpy library and we square each of the differences we've computed. So the next function and the last one that we will implement will plot the errors using a contour plot. And if you have experience with contours, the contour function, the contour f function from Python, it only works with data along a grid, and that's something we don't have. We have randomly sampled data which needs to be interpolated onto a grid. So before I implement the function, I would like to discuss that. So let's get back to the drawing board first. So what we have is a two-dimensional feature space. Let me just plot that. So we have x1, and let's assume that there is a grid over this two-dimensional feature space. So you have a grid which is structured, and this grid has the corresponding nodes, which are shown here in green. So these are the nodes of the grid. So what the contour f function wants is the value of x1, x2, and the value of the prediction at this green point. And this is something we don't have. What we did initially, if you remember, was to sample the input space randomly, right? So we might have, for example, the values of the predictions at these red points. So before we can use before we can make a contour plot, we would like to compute the values at these green points, and the way we do that is using interpolation. I will just directly be using the inbuilt functions available in Python. And what this inbuilt function does is that it performs interpolation using the so-called nearest method. So you take this green point and then you try to find which red point is the closest to this green point, and then this green point takes the same value as that red point. So this green point is the nearest to this red point, so the value at this green point, or the label value, would be the same as the label value at this red point. So this is what the function would do. So now let's get back to the code. So I will first be implementing the function that outputs or interpolates the values, the randomly sampled values onto a grid. The input to this function is the feature vectors of the randomly sampled values, which are collected in X, and the corresponding labels, which are in Y. So let's first create a grid. And to create the grid, we will use something called a mesh grid function from NumPy. And first we take the minimum value of the first input feature, then we take the maximum value of the same input feature, and with this we create a grid. And after we've done this, we will place 100 points along the x1 dimension, and then we do the same for x2. So sorry, this should be 0 because we took values from the first input feature, and we do the same for the second input feature. And then finally, this is the core of the grid function we want to interpolate. So we do that with the help of a function called grid data, and the grid data function takes as input x, which are the original values, y, which is the label on these original values, and then finally we provide the node locations of our grid, so that interpolation could be performed with the help of the nearest method, which we just discussed. what we will return from this function is x1 grid, x2 grid, and finally the labels on these grid points we have placed. So with this grid function in place, we can finally generate a plot using using contours, and this plot would take the count truth labels and the predictions. So first we initialize a figure object, which is same as any other plotting routines you might have seen. Then we compute the difference between the predictions and the ground truth label, and we take an absolute value of these because we want to plot the absolute error over a two-dimensional input space. And before we could plot that, we need to interpolate these values along a grid. That's what we do here, and the input to this grid function was x test and diff. So we need to also input the input features to this function. An additional thing we need to do is to remove the third dimension. So diff here would be a column vector, and that would be inappropriate for the grid function. So we remove that additional column dimension using Rabble. And finally, we can plot everything. The fit model class, and the only thing we now need to do is to fit a model using the class we've implemented. So first we will initialize our class. Now I'll set the value of k to 3 just for demonstration purposes. In practice, you would set this value using a validation set, because this is a hyperparameter of your model. So the next thing we would do is to get predictions corresponding to the k nearest neighbors, with k being equal to 3. And we would do that with the help of the get prediction function. I'll just copy paste that here. So this get prediction function takes as input the training points and the features corresponding to the testing points. And once we run this, we'll have the predictions at these test points. So the next step would be to plot the errors we are getting from this approximation, and we would do that with the help of generate data plot routine. So this routine takes as input the features at the test point, the output, the true output labels at the test points, and finally the predictions we have from this approximation here. And once we run this, we should be getting a contour plot of the errors, and you can see that the error is pretty much randomly distributed. And if you compare it to what we did for linear regression, so in case of linear regression, there the errors were small, and that was mostly in the mid region here. In this case, because kNN is mostly a nonlinear approximation, it leads to very similar error along the entire input domain. So that wraps up